Greetings. We are going to continue our discussion on light atom interactions, and in particular we will modify and upgrade the model that we have used in the previous discussion. So, we described the light matter interaction using the semi-classical Hamiltonian, which essentially treated the atom as a quantum system, so that its bound states are discrete, which is an essential signature of quantization of a bound system. Unbound system have got continuum states, but bound states have got a discrete eigenspectrum. So, you have the bound state of an atom, and we considered for a two-level system, so that a two-level atom interacts with an electromagnetic field described as a wave, not as a quantum field, and the interaction drives transitions from the ground state to the excited state, and also from the excited state to the ground state. Now, we do know from Planck and Bose and Einstein that there are quanta of electromagnetic radiation, and these are the quanta that we call as photons. And the photon character of the electromagnetic field was not explicitly considered in the semi-classical description. What it led to was the Rabi oscillations, and we had these very nice oscillations, but the oscillations required the interaction to be given, to be available all the time. So, if the electromagnetic field was not there, this interaction would not take place. And in particular, if the atom goes in an excited state and there is no longer an electromagnetic field because it has already been absorbed, then the atom would have no mechanism to come down in that description. So, that is a problem over here. And then you will have the quantum description of the electromagnetic field, and this belongs to the general area of what is called as quantum electrodynamics. This was developed basically by Dyson, Feynman, Schwinger, and Tomonaga, and it all is based on the work that began with Planck and Bose and Einstein. And I would like to suggest some references for this part of the topic, for this part of the discussion. So, there are two very nice books, Jerry and Knight, which was published in 2005, and another book by Fox, published around the same time in 2006. The first is Cambridge University and the second the Oxford University Press. Both came around the same time with somewhat similar titles, Introductory Quantum Optics and Quantum Optics and Introduction, all right. And then there are very nice articles which are available. Again, an article in which to which Peter Knight has contributed, an article by Shore and Knight in 1993, a slightly older article. But then there is a more recent article which I have used rather extensively, an article by Matteo Bina, which is in the European Physical Journal, so in the special topic series. It's like a tutorial on the Jaynes-Cummings model, which I have used quite extensively in the discussion. And then a more recent paper on several ways to solve the Jaynes-Cummings model by a group of authors in Applied Mathematical in 2015. But then there are very nice lectures on the YouTube which are available by Professor Wolfgang Ketterle, who got the Nobel Prize for achievement of the Bose-Einstein condensation. And this is a part of his lecture course that he delivered at MIT. And now that I am giving you this reference, essentially it means that you can attend to his lectures and you don't have to listen to me. But anyway, these are it's a great lecture course by Professor Ketterly, and I strongly recommend that. But we will do our tiny little bit. So we are now working with a two-level system, and we have to come to terms with the fact that if you accept that the excited state has got a certain width and a certain lifetime, then there will be a decay, and there is a spontaneous emission, and this would damp the Rabi flopping, okay, the Rabi oscillations. You have in the Rabi oscillations, we described the generalized Rabi frequency. You remember that when it was detuned, right, when it was slightly off the resonance. And what the detuning did to Rabi oscillations was that the flopping frequency increased, okay, because it is the square root of the sum of the squares of the Rabi frequency plus the square of the detuning difference. Omega tilde was the difference between the electromagnetic energy and the energy difference between the two states. So the flopping frequency increased, but the flopping amplitude of oscillation, it decreased a little bit as you move away from the resonance, because it is scaled by the ratio omega r over omega tilde. Okay, so omega r is the Rabi frequency and omega tilde is the generalized Rabi frequency. So this two-level problem is very similar to this Zeeman effect kind of thing. It's a classic, the whole mathematics of this two-level problem is completely identical to that of the Zeeman effect mathematics, the quantum mechanics involved in the Zeeman effect. And you know that two states which are degenerate, they split in a magnetic field, one for spin up and one for spin down for the in the case of the electron spin, and the splitting is proportional to the magnetic field, and the same thing happens to a proton magnetic moment, because that also has got a magnetic moment which has got a similar interaction, except that the gyromagnetic ratio is different for the electron and for a proton, but the basic phenomenology is essentially the same. And the energy difference between the two levels is the Larmor frequency in units of h cross, and that depends on the magnitude of the magnetic field which is employed. Now, what the magnetic field does to the magnetic moment of either the electron or the proton, whichever it is it puts it in a state of precision. Okay, the angular momentum changes, and basically it is the direction of the angular momentum which keeps changing because of this torque, which is mu cross b. Okay, so as a result of this mu cross b and mu, the magnetic moment is proportional to the angular momentum. The proportionality is the gyromagnetic ratio, and this torque causes a precision in the laboratory frame, okay, at the Larmor frequency, which is minus gamma b0, as you can see, right, and omega, which is minus gamma b0, is what is called as the Larmor frequency. So this is actually a quantum effect, because you cannot pin down the three components of the angular momentum simultaneously. Okay, any two do not commute the projections of the angular momentum, and as a result of this, you really cannot have the x and y components simultaneously determined. So in a semi-classical model, this is indicated by this precision at the Larmor frequency, and you recognize from this a relationship that you have seen in an earlier course on mechanics, because essentially you have got the time derivatives in a lap frame and in the rotating frame, and these are related to each other through another term which gives you the operator equivalence. So, we discussed this in this, this is equation 3.13 in the foundations of classical mechanics, and essentially this is the expression that you invoke when you deal with the Coriolis term, right. So, in the Coriolis term, when you carry out the transformations from an inertial frame of reference to a rotating frame of reference, when you do this analysis and you take the time derivatives of position vector and also the velocity, you get this additional effect, and you get exactly the same kind of relationship over here, that you have this omega, this angular frequency, and then the cross product with the magnetic moment, and this is the time derivative of the magnetic moment in the rotating frame of reference, which will give you the time derivative of the magnetic moment in the inertial frame, and this is given by gamma mu cross B0. So, it is exactly the same kind of relationship, and you can extract the mu dot term, which is the rate of change of the magnetic moment in the rotating frame, which is given by this term minus this term. Okay. So, this term is what I have written here, except that I have moved gamma to be multiplying B0 rather than mu. It leaves the value of the cross product invariant. So, I have got mu cross gamma B0, and this comes out on the right side with a minus sign, but I write it as mu cross omega instead of omega cross mu. Okay. So, that the sign reversal is taken care of, and now I can take mu as common, and I get the cross product of mu with gamma B effective in the rotating frame of reference. So, the effective magnetic field is the sum of this B0 and omega over gamma. Okay. So, that is the equivalence that we get. In the rotating frame, the magnetic dipole would seem to experience an effective magnetic field, which is the sum of the one that is applied plus a term. So, this is like the pseudo term that we get in the Coriolis analysis. So, it is interesting to see that if omega happens to be equal to minus gamma B0, which is actually equal to the Larmor frequency, the angular frequency vector, then the effective magnetic field would be 0 in the rotating frame. Okay. And now, if you apply a transverse magnetic field, okay, which is orthogonal to the original field that was applied, then you can resolve it into, if this is linearly polarized, then you can write it as a superposition of two rotating fields, okay, with rotational polarization, one clockwise and the other anti-clockwise. And if you see this figure, this red and the blue circles are right on top of each other. They have been slightly displaced in this figure just to show that there actually are two, but essentially they are right on top of each other, and you can see that the vertical components would cancel and the horizontal components will add up. Okay? So, which means that this blue arrow and the red arrow will add up to give twice their length, which is the length of the black arrow, which is the magnitude of the horizontal linearly polarized magnetic field. Okay? So, the magnetic field, which is the transverse magnetic field, can be broken into two magnetic fields, one which is rotating clockwise and the other rotating anti-clockwise, counterclockwise, but both of half the amplitudes. So, this is the kind of resolution we have discussed this model earlier also, and So, now in the laboratory frame you have got the counterclockwise field which rotates exactly in step with the precession with the precessing dipole. Okay? But you have the other field which is rotating clockwise, it will be seen to be rotating at twice the angular frequency, and it would be that much farther off from any resonance energy, okay, because it will be rotating at twice the frequency, whereas this one would be rotating exactly in step with the precessing dipole. So, this is what we have got. The effective magnetic field is 0 as we have seen, and when the transverse magnetic field B perpendicular is applied, then the effective magnetic field is just the half this magnitude of the counterclockwise component, and this is always along the rotating Ex direction. So, that itself is rotating, mind you, okay. So, which is why it carries a superscript r to remind us that it is rotating, right. And what it really means that in the rotating frame the dipole will precess about the x axis of the rotating frame, okay, at an angular frequency which is minus gamma times b over 2, which is this b perpendicular over 2, right. So, that will be the precessional angular frequency, and how much would the dipole change? Because of this precession it would tilt, right, and the tilt angle will be depending on for how much time you have applied that pulse, and depending on the pulse duration, which is tau, you will have the dipole to change through an angle theta, which is this duration times this gamma b over 2, which is the angular frequency. For example, if you have a pi pulse, then this duration tau is subscripted by pi corresponding to the pi pulse, and you see that this duration will have to be 2 pi over gamma b. In that much duration it will tilt it through an angle pi, okay. So, after the pulse duration, if you switch it off, the Larmor precession would continue, but the polar angle will now be different because the pulse would have tilted it, okay. So, that is the dynamics of the magnetic moment over here, and here are a different situations. So, at time, depending on how much time duration do you apply the pulse, okay. So, this is a work, famous work due to Rabi in 1939, and this is for t equal to 0, you have got an alignment along the z prime axis, and then if you are looking for a pi by 2 flip, then you need to apply the pulse for pi over gamma b perpendicular, because if you multiply gamma b perpendicular by 2 by this time interval, you see that theta turns out to be pi by 2, right. What do you need if you want theta to be pi? If you want to flip it, then you have to apply this for 2 pi by gamma b perpendicular. If you want to take it 3/4 of the cycle, then it will be 3 pi by gamma b perpendicular, right. Okay. So, all you have to do is to multiply that time interval by gamma b by 2 and see how much angle it changes through. And if you want a full circle, which is 2 pi, which is the completion of the Rabi cycle, right, then you have to add another quarter of the time. So, that will be 4 pi by gamma b perpendicular, and then you will have a 2 pi rotation and you would have completed the Rabi cycle, okay. So, this is because we know what the rabbi frequency is. It is gamma b by 4 pi, and this tells you, depending on the duration of the pulse, what through what angle the magnetic moment would be tilted. So, this is the rabbi oscillations, and these are nice and undamped, as if they are going to stay forever. But then there is damping. And what is damping? Damping is basically losing energy to some unspecified degrees of freedom. So, we have considered this two-level system and the interaction with the laser light. But then in a real system, there may be additional surroundings with which the system interacts, and as a result of that surroundings, some energy will be leaked into this additional degrees of freedom, and that will result in damping. And depending on the extent of damping, these rabbi oscillations, which look so nice and continuing by these dotted oscillations, they will actually get damped out depending on the extent of damping. Okay? And they will get damped out, and in due course of time they would actually even die out. So you have this the population probability C2T is the probability amplitude that the atom is in the excited state 2. Its modulus square will give you the corresponding probability, and that probability will not remain completely oscillatory because its amplitude will progressively diminish. Okay? So, this is the damping that we have to take into considerations, and this is the expression that we had without damping, but now with damping this relation gets modified. And this modification was taken into consideration by Felix Bloch using a phenomenological model. Okay, using a phenomenological model, Bloch took into account damping, and damping was admitted in Bloch's analysis by considering relaxation effects of two kinds. One is the transverse relaxation effects, and the other is the longitudinal relaxation effects, and accordingly you have the spin-spin relaxation and the spin lattice relaxation. He considered it in the context of the nuclear Zeeman effect, which is the same mathematics and the same quantum mechanics essentially. So, there are these two relaxation modes that Bloch considered, and he introduced damping through these relaxation times. One is T1, which is the longitudinal, and the other is transverse, which is T2. So, the relationship without damping, which is d mu by dt equal to gamma times mu cross B naught, this all the components x, y and z components are not given by components of this equation, but they are diminished by a relaxation mechanism. And that relaxation mechanism Bloch considered to be proportional to the component of the magnetic moment and scaled by a certain characteristic relaxation time, which was T2 for the transverse components for the x and y. So, we are considering the magnetic field to be about the z axis, and then the component along the z axis will be scaled by T1, but then it will be proportional to the difference between mu z, the z component of the magnetic moment, and mu naught. Okay? So, these are the Bloch equations and or Bloch phenomenological equations, and after long enough time one would expect that mu x and mu y would go to 0 if the system is completely relaxed, if t goes to long times, and this is what you would expect, but this is again a semi-classical model. Okay, this is not a quantum model. So essentially we have two relaxation times over here, one that you call as the transverse relaxation time, which goes for the x component and also for the y component. All right, so this one applies to both the x and the y components, and for the z component you have got the longitudinal relaxation time. So what are the damping mechanisms which are involved? What will the damping do? You have spontaneous decay to lower levels, right? So the population will decay because of this mechanism. So the population is not going to stay the same because of this, and this will destroy the coherence. So you expect a certain coherence to be maintained between the light and the atomic states, but then this coherence will be destroyed, and this will come as a hindrance to the Rabi oscillations. So this is an effect that you cannot avoid, and this will depend on the lifetime of the excited state. So you can have decay from two processes. One is a radiative decay, that when the atom goes from an excited state to a lower state and light is emitted, a photon is emitted, then you have a radiative decay. It can decay not only to this level, but if selection rules permit, even to a lower level. So there may be a discrete spectrum. So this two level system may be a part of a multi-level discrete system, okay, and then the atom can decay not just to the immediate next level, but also to one of the lower levels in case the selection rules would permit that. So you can have a radiative decay, but there may also be non-radiative decay. There may be some other collisions, for example, all right, and this collision may also nudge it and destroy the coherence. So you have this radiative component and the non-radiative component, and the overall lifetime you can write as a product of tau r, tau nr divided by sum of the two. But then you also have transverse relaxation, okay, and the transverse relaxation will also contribute to the dephasing, okay. So you can have transverse relaxation which will also contribute to the dephasing. So now you have this radiative and non-radiative components which I mentioned when we were discussing the previous slide, and you have this radiative decay to this level, but you can also have a radiative decay from here to a lower level which is a non-resonant level. And once it gets off the resonance, then it cannot come back to the family of cycles which give you sustained Rabi oscillations, okay. So this is the hindrance to Rabi oscillations, and then you can have collisions which also contribute to dephasing, not necessarily resulting in population changes, okay. So the collision simply nudges the atom, all right, changes its phase without actually influencing the atom to undergo a transition, okay. So without a transition, so if there is no transition, then the population of the two levels does not change, but it has lost its phase coherence because of the nudge, because of the collision. So you have these two components, T1 and T2, the transverse component as I mentioned, and the dephasing takes place through these two mechanisms. One is the non-radiative collisions and the second is the radiative transitions, and the radiative transitions again are of two kinds. One are resonant radiative transitions and the other are non-resonant transitions which can send the atom to an even lower discrete state if there is one. Okay, so now you have got these contributions to overall dephasing because one involving population decay and the other which does not involve population decay just because of collisions, and you can define this relation which will give you the overall relaxation time, and this relaxation time, this you can write T2 as a product of 2T1 and T2 prime by T2 prime plus 2T1. So, the 2T1 is just a matter of definition. You could have written just T1 also. It is a matter of just scaling by a factor of 2, and this is some authors do it one way and some do it in the other way, but this has been done using the convention adopted in the book by Fox on quantum optics, which is in fact different from that adopted in the very widely cited paper by Allen and Eberle. There is a difference in the factor of 2, which is also a very commonly referred to paper. So, when you actually do the calculations, you have to be careful about this. So, there will be a difference in the factor of 2, but otherwise it is the same thing. So, what is the main factor of decoherence? It can be either collisions or it can be the lifetime of the excited states. It could be both, but one can be dominant, one of these can be dominant, and when T2 prime is much smaller than T1, then collisions is the dominant reason for decoherence, whereas when it is the other way around, when T2 prime is much larger than T1, then it is mostly the lifetime of the excited state which is the dominant factor. So, here we are. So, remind yourself of our previous discussion. So, we described the interaction between the atom and the electromagnetic field using a semi-classical Hamiltonian. The semi-classical interaction was represented by this D dot E type of term. D is the dipole moment and E is the electric field, right. So, epsilon over here, or what looks like epsilon over here, this is the electric field, and the interaction between this electric field and the dipole gives you this interaction between the atom and the light and light. And the Rabi frequency was defined, it was proportional to the dipole moment and also the magnitude of the electric field. That is how it was defined. If you remember, this is the single photon Rabi frequency. But the problem with this semi-classical description is that it requires the Hamiltonian, the classical Hamiltonian, the semi-classical Hamiltonian, which is D dot E. So, that E has to be there, that electric field always has to be there. If you switch it off, you cannot have this interaction. Okay. So, you cannot have this interaction, and the atom will not undergo a transition from the lower state to the excited state, nor from the excited state to the lower state. And then you if in a number of atomic systems in electromagnetic field, even if you set in the Rabi oscillations, they are going to die out because of this. Okay. So, that dying out of Rabi oscillations is sometimes called as the collapse, but then there is also a revival which is possible, and that is possible because the model that we have used over here is not quite correct. It is semi-classical, and we really need a quantum description of the electromagnetic field. Okay. So, in the absence of the electric field, emission of a photon would not be possible in a semi-classical model, okay, because you have that driving term which couples the atomic dipole to the electromagnetic field. So, this problem is solved by invoking quantum electrodynamics, and in particular what is called as cavity quantum electrodynamics, by considering this system in a cavity. And we are now led to this wonderful theory, it is a beautiful theory, quantum electrodynamics, developed by Dyson, Feynman, Schwinger and Tomonaga, and along with the work of Glashow, Salam and Weinberg, it is an integral part of what we now call as the standard model of physics. Okay, the standard model of physics is predominantly the quantum electrodynamics plus this additional contribution for which Glashow, Salam and Weinberg got a Nobel Prize, and so this is the quantum electrodynamics. It is raised on the work of Planck and Einstein and Dirac and Feynman and of course Bose and Einstein. Okay? So this is the quantization of the electromagnetic field, and this model was used even at the time of the early works on the black body radiation. Rayleigh and Jeans considered harmonic oscillators, right? And then Planck came up with this idea of a quantum of electromagnetic radiation. And now the quanta of the electromagnetic radiation, which are photons, these are essentially Bose particles and they follow the Bose-Einstein statistics. And you need to use the field quantization, which is the second quantization in a certain sense, right? And it is described by the boson creation and destruction operators. So the second quantized creation and destruction operators, and I have discussed this in a different course. I have given the reference over here with which is a special topics in the theory of atomic collisions and spectroscopy, STI tax. In the unit 2, I have discussed this, so I am not going to spend any time redoing the second quantization as such. You can go through this earlier material, but essentially you now have the creation and destruction operators for two types of particles. One is the Fermi particles and the other are the Bose particles, and here we are dealing with bosons. And the creation operator F dagger and the destruction operator F satisfy these commutation rules, that for the mode R and mode S, the Fr comma Fs dagger, which is Ff dagger minus F dagger F, that is the usual commutator, right? And this will be equal to the Kronecker delta. It will be 0 if the modes are different, but it will be equal to unity if the modes are the same. Okay? And then the creation operators commute with each other and the destruction operators also commute with each other. And you have a system of oscillators for which the classical Hamiltonian is just p square over 2m plus half m omega square x square. As we know, we consider a simple one dimensional system. This is the Hamiltonian in the first quantized notation, but then in terms of the second quantized operators, you define the F and F dagger in terms of position and momentum operators. Okay, because now you are dealing with operators and you can use these position and momentum operators to define the creation and annihilation or the destruction operators. And if you use this algebra, and I will just refer you to this previous course, the unit 2, in which these things have been discussed at some length, but I will remind you of some of the more important results that we are going to find immediately useful. So if you now determine F dagger F operator, then you just carry out, you write the F dagger and then the F, and now multiply these out, always keeping track of the fact that the position of these operators is important, because position and momentum do not commute with each other. So whatever positions they have, so like in this term you have xp, whereas over here you have px. So you can combine these two terms to find the commutator of position and momentum, and we know what that result is from the uncertainty principle, right? From the uncertainty principle, you know that it is IH cross, and you can write this f dagger f. You can do some simplification, cancel off the h cross, then I square will give you minus, and you get a minus half over here. And this Hamiltonian for the simple harmonic oscillator you can write in terms of the creation and destruction operators like this. Okay? So essentially you have this expression for the Hamiltonian, the second quantized Hamiltonian, in terms of the creation and destruction operators, which will be f dagger f. So f dagger f is the number operator. Okay? So we are going to use this machinery. You can write the position and momentum operators in terms of the creation and destruction operators, and you can do the inverse relations, which is writing the creation, the destruction operator and the creation operator in terms of the position and momentum, right? And using these commutation relations, you have this simple result. So now we are going to consider light in a cavity. So it is going to remain trapped. It will get reflected between the two mirrors, and the cavity is between these two mirrors. You have got total reflection from one mirror, and from the other mirror you have only a partial reflector, so that light can be extracted out of it. Okay? And this is optically machined cavity, so the distances are really very accurate, very exact, and you can now quantize this system, the electromagnetic radiation in this cavity, and then depending on how much energy there is in the field, you will have a certain number of photons in the cavity, which is an integer number of photons, which will be an eigenvalue of the number operator, which is f dagger f. So these are well known results from second quantization, quantum mechanics of second quantization, and you can see that if n is an eigenstate of the number operator, then f operating on n is also an eigenstate, but it belongs to the eigenvalue n minus 1. So this helps you determine the normalization, because using this relation, if you find the normalization of f of n, then this will be given by the projection of f of n on its adjoint, which is f dagger adjoint n, right? And you can see that this f dagger f being the number operator, this will be equal to n. So that tells you immediately that f of operating on n will give you the square root of n times the n minus 1. So it is a destruction operator, it destroys one particle, you get another Fock state corresponding to one number less of the number of bosons, in this case the number of photons, but then it will be scaled by the factor root of n. Okay? So this square root n is an important factor that you must carry in your analysis. Similarly, you can use these relations. So you find what is nf dagger, which is f dagger 1 plus n, and you can now use this to determine the norm of f dagger n using the same kind of reasoning. It is exactly the same kind of argument over here, and notice that the norm of f dagger n will be f dagger n's projection on its adjoint, which is f n, and this will be equal to this 1 plus n, right. So it means that when f dagger operates on n, you get a state with one extra photon or one extra boson. These are true for all Bose particles, but then the state will also be scaled by root of n plus 1. Okay, that is the normalization that you have to carry. And now we have to quantize the electromagnetic field. So in free space we know that this is described by Maxwell's equations. Okay. and the fields are expressible in terms of the potentials, the vector potentials, right, and you can always work in the Coulomb gauge. So, you have these potentials which satisfy the wave equation, and the solution to the wave equation is in terms of this. You can apply boundary conditions and so on, but essentially you are having a solution to the vector potential over here, and given this solution you can determine the electric field, because the electric field is nothing but the negative of the time derivative of the vector potential. So, you just find the time derivative of the vector potential and get the electric field. Likewise, if you find the curl of the vector potential, you will get the magnetic field. So, now you have got the electric and the magnetic field. For this cavity, you can consider this cavity to be in some sort of a box, okay, and in this box you will have a certain amount of electromagnetic energy which you have expressed in terms of the electromagnetic fields E and B, but now you have to express it in terms of photons, which are the quanta of the electromagnetic fields. Okay. So, this is the total energy in the electromagnetic energy in that box, and this is just the integral of the magnetic field energy density and the electric field energy density. So, these are well known relations which I am sure you are familiar with, and you can write this in terms of the simple harmonic oscillator states by using the position and momentum operators, as we have discussed this idea earlier. So, we introduce the Q and the P operators. We define them using this relation that we have over here. So, we define T and T star in terms of Q and P. We have got the total electromagnetic energy, and quantization we will invoke through the usual uncertainty relation, which we already know for the position and momentum operators, but the role of the position and momentum operators over here is completely formal. We just use them to define the quantization of the electromagnetic field. All right. So, you are quantizing it through the uncertainty relation for position and momentum. You can also do it using dimensionless operators, uppercase Q and uppercase P. All right. So, this is just a matter of definition. These are quadratures which can be defined, and now you have got essentially the same uncertainty relation which is expressed, which involves the angular momentum, now appears without the angular momentum, but it is essentially the same physics in it. And now the Hamiltonian which we know is given by this F dagger F plus half h cross omega. In terms of the second quantization operators, Q and P are the quadrature operators, and we are going to consider the cavity to have electromagnetic excitation in a single mode. So, we have a single mode Hamiltonian, means when you have an electromagnetic field you will have all kinds of modes which are available, all right. But we are going to consider the interaction between an atom and a single mode electromagnetic radiation with a single photon. Okay? So, it is a quantized electromagnetic field with one photon. So, the atom is in the ground state in the cavity and there is one photon which is available. That photon can be swallowed by the atom can get excited. Now, you have got the atom in the excited state, but zero photon. There is nothing else. There is a single mode, single photon, and there is no electromagnetic field. So, now the semi-classical Hamiltonian would fail over here because it needs that electromagnetic interaction. Now, once the atom goes into the excited state, there is no longer any electromagnetic field present in the cavity, but the atom is in the excited state. But then we are going to develop the second quantized formalism, which is the Jaynes-Cummings model, and you will see that it provides for a de-excitation and the Rabi oscillations. So, it is a single mode Hamiltonian that we are going to consider. So, you have this relationship. We earlier wrote T and T star in terms of Q and P. You have F and F dagger also in terms of Q and P. So, you can now write T and T star in terms of F and F dagger, and once you do that, you can write the E and B in terms of F and F dagger. So, now you have achieved quantization of the electromagnetic field. The electric field and the magnetic field are written in terms of the second quantized creation and destruction operators. So, obviously, as you can see, there is some algebra involved, which is to write one in terms of the other, right? T and T star in terms of Q and P, F and F dagger also in terms of Q and P. Therefore, you can write T and T star in terms of F and F dagger, and now you can write E and B in terms of F and F dagger. So, that algebra is something that I leave it to you to be done as an exercise, but it is straightforward substitutions and nothing else, all right, just usual linear algebra, nothing else. So, you have got the electromagnetic field which is now quantized, and mind you, this electromagnetic field is in the cavity, okay. So, when you have travelling waves, the electric field and the magnetic field are always in phase, but in a cavity you have standing waves, you do not have travelling waves, and then you must apply the interface conditions for the Maxwell fields. And when you apply that, it turns out that the electric field and the magnetic field will not be in phase. They will actually be orthogonal. There will be a pi by 2 phase difference. And this is to be expected because standing waves are not transporting energy. Travelling waves transport energy, standing waves do not. Okay? So, you have this off phase relationship between E and B, and now you have written the electric field and the magnetic field in terms of the creation and destruction operators. You can immediately see that the expectation value of the operator E, this is now an operator, this is the second quantized operator, in an occupation number state will be 0, but that because F dagger will create a particle which will be orthogonal to the previous state, F will destroy a particle which will also be orthogonal to the previous state, right. So, the expectation value of E will be 0 in the occupation number eigenstate, but that of E square will not be 0. You will get a non-zero value which is n plus half times h cross omega by epsilon 0 b. So, notice that here if you consider E square to be given by this, the electric intensity itself would in a certain sense be given by the square root of this. And for vacuum, for n equal to 0, there will be a factor of half, okay. So, you have got half h cross omega over epsilon 0 E, and this will be the electric field per photon. And what you can do is exploit the fact that the volume V comes in the denominator. So, if you make that volume V smaller and smaller and have a tiny cavity, you can have the electric intensity in that particular mode go huge, and it becomes overwhelming and becomes the dominant factor. Anything else will not be of any relevance. So, this is what gives you a single mode field cavity QED, because you have made the cavity small enough so that only that particular mode which survives in that cavity, okay, will be of significance. So, I will take a few questions and then we will continue the discussion from here in the next class.